All right, guys, I know this is a little bit different than what you're used to. I'm sorry that you're in this position and that your teacher's not here with you, but that's okay. We're going to get through. So I was told that you didn't already have information about areas of similar figures. So I had some stuff that I thought I'd pull up. Remember, when you studied similar figures, that similar figures have a scale factor, like a ratio that compares the length of one side to the length of another. I don't know if you remember that. Um, so the ratio of the perimeters was pretty much the same thing. That doesn't change. But for area, it is very different. The ratio of the areas is a squared over b squared. So it is a little bit different. But as long as you keep that in mind, you really can't go wrong. There's not much to this at all. So we're going to find the ratio of the similar figures, trapezoids at right, are similar. The ratio of the lengths of the corresponding sides is 6 to 9 or 2 to 3. What's the ratio? And notice that you always want to pay attention to what they want in the numerator. So they're saying smaller to larger. So remember that's numerator. Excuse me, and this is denominator. So smaller to larger means we're going to put the 6 over the 9 again, which is still just 2 to 3. Remember, that's the same. It's for same for perimeter as it is for the side length. And why is that? Because it's a linear measurement. Just like a side length is a linear measurement, perimeter is also a linear measurement. However, the ratio of the areas is a little bit different. So the scale factor, remember that the scale factor is still just 2 to 3. You don't have to use the 6 and the 10. You can use the 2 to 3. But the ratio, because we're not actually finding the individual areas right now, we're actually just talking about the ratio of the areas, right? So we're going to say 2 squared over 3 squared, and the ratio of the areas, smaller to larger, again, smaller goes in the numerator, and larger goes in the denominator. I know you've already done all this, so that's going to be 4 over 9. Got it? And that's about as good as it gets. So we'll just practice that on a couple of different problems. On the next page, we're going to find the area using similar figures. Area of the smaller regular pentagon is about 27.5. What's the best approximation for the area of the larger regular pentagon? Notice the information you're given. You're given a side length in the small pentagon, and you're given a side length in the large pentagon, right? Okay, so let's find the scale factor, and the scale factor is going to be 4 over 10, right? Which is just going to reduce to 2 over 5. But then we want to find the area of the larger regular pentagon. So remember, I put the smaller one in the top and I put the larger one in the bottom. No particular reason why. If you're going to flip it the other way, it's okay. But if I'm going to use this, and remember that this is going to be comparable to the a over b, then I'm going to have to do a squared over b squared. Because I know this area is 27.5, this is what I'm going to have to use to figure it out. So I'm using 27.5 as the area of the smaller, so I'm going to put that in the numerator, 27.5 over x. X just represents the area of the large pentagon. That's all it is. Okay? But then I'm going to take my scale factor, which is the 2 over 5, and I'm going to say 2 squared over 5 squared equals 27.5 over, that's 0.5, over x. So 4 over 25 is equal to 27.5 over x. And then I'm going to cross multiply and get 4x equals 687.5, and then divide that by 4, and x is equal to 171.875. So the best approximation for the area, if I change that to area, is for the larger area pentagon is going to be about 172. So that would be the answer that I would choose up here would be choice C, if a multiple choice question. All right, now we're going to try another one. You don't actually have answer choices here, but you do have some information. So again, we know the side lengths. We know the side length of a smaller is 16 inches, and we have similar figures, and a side length corresponding side in the other triangle is 28 inches. Obviously, I didn't really provide enough information about the similarity, but I'm going to ask you to go ahead and assume that this correspondence is accurate. If you want me to, then I'll just put in some information to indicate precisely that those triangles are similar. Okay. So we want to talk about finding the area of the other figure, and what we have known is that the area of the small triangle is 54 inches. So this area is equal to 54 inches squared. All right. Same thing again. I'm going to find the scale factor. The scale factor is going to be equal to, if you want to put the smaller over the larger, then I'm going to say 16 over 28, divide them both by 4 and get 4 over 7, right? Okay, so the scale factor is 4/7, and then I'm going to use that and the idea that the ratio of the areas is a squared over b squared. And so I'm going to say 4 squared over 7 squared is equal to, and remember that this was the smaller triangle, and that is the length that I put in the numerator, so I'm going to say 54 over x. X is equal to area of larger triangle. Got it? All right, so 16 over 49 is equal to 54 over x, and cross multiply 49 times 54. So 16x is equal to 2,646. Divide by 16. X is equal to 165.375, and that's an exact value, which is just fine. It does say, though, to the nearest whole number. So if I have to approximate to the nearest whole number, then the area of the large triangle is approximately to the nearest whole number. I'm looking at the ones place, so 165 inches squared, because the 3 just means that you're not going to round up. All right, moving on. In general, you're still doing the same thing. The triangles are similar. What's the scale factor? What's the ratio of the perimeters? So this is the basic thing. Just remember, in this case, now we're looking for the ratio of the perimeters, and we don't have the scale factor yet. So this is what we already know. We know the areas of the two similar triangles. So we know that the small triangle has an area of 50. We know the large triangle has an area of 98 centimeters squared. Okay? We need to know the scale factor because the perimeter for the perimeter, the ratio of the perimeters is going to be the same as the scale factor, right? This is same as scale factor. If you go back to the first page, this is exactly the same as scale factor. Remember that one side, when you compare two sides, that they are linear measurements, and perimeters also linear measurements. So let's make a ratio right here. Let's compare the small triangle. I'm going to compare the small triangle to the big triangle. So I'm going to put 50 over 98. And before I do anything else, I notice that it's reducible. So I'm going to go ahead and reduce, right? And when I reduce, then the ratio that I get is going to be, if I can divide them both by 2, then I'm going to get 25 over 49. What's nice about that is that those are both perfect squares, right? So if you consider that this 25 kind of represents a squared and the 49 represents b squared, then you can just take the square root of each of those numbers separately, and you can tell me then that the scale factor is equal to 5 over 7. And just like the scale factor when you're comparing the sides, the same thing. So this is still going to be the ratio of perimeters. That's the same thing as the scale factor, right? Same exact thing, 5 to 7. All right. Next problem, we want to find the scale factor and the ratio of the perimeters for two regular pentagons with areas of 50 inches squared and 162. So again, we have area. So remember that if we're starting with area, we're really starting with a squared over b squared is what we're going to do. So I'm going to say 50 over 162. I'm going to do the exact same thing. I got to reduce. excuse me, reduce, and I'm going to get 25 over 81. That's lovely because they're both perfect squares, makes it a little bit easier to work with. So that means that if I take the square root of the top and the square root of the bottom, then A would be 5, B would be 9, right? Okay, so the scale factor is equal to 5/9. The ratio of perimeters is also 5/9. Remember that those are one and the same because they're both linear measurements. Got it? Very last problem. Here we go. Okay, we've got corresponding sides of two similar parallelograms in the ratio of 3 to 2. The area of the larger parallelogram is 108 inches squared. Find the area of the smaller parallelogram. Okay, so we know that if we compare the sides, 3 over 2, 3 is like A and 2 is like B, right? Okay, when you think about a scale factor, because that's what that scale factor was represented by, okay? But we know the area of the larger parallelogram. So when you're looking at this scale factor ratio, remember that you're going to have to end up doing A squared over B squared. In every other problem that we worked, we always put the smaller one on top, but it really doesn't matter. What matters now is we pay attention to the fact that this 3 is up top, right? So this represents a reduction of the large parallelogram. And I'm just going to draw a parallelogram there. Okay, so be careful that your 108 now actually has to go in the numerator right here. Got it? That's kind of a big deal at this point. And then what we're going to be looking for is we're going to be looking for x, and x equals the area of the small parallelogram. Just going to abbreviate, sorry. Okay. All right, if you ever don't understand my abbreviation, then you're going to have to let me know so I can fix that. All right, so we already know the scale factor is 3 to 2, so now I'm going to say 3 squared over 2 squared equals 108 over x, 9 over 4 equals 108 over x. So 9x is equal to, that should be 432, and x is equal to 432 divided by 9, which is 48. So the area of the smaller parallelogram is equal to 48 inches squared. And you're done. That's pretty much it. That's all there is to finding the areas and finding the ratio of the areas.